Numeric derivatives. So we have to talk about what is a derivative, and it starts with the concept of a rate of change. So if you remember back in algebra, you learned about the rate of change of a function, or if you're looking at the graph, you would have called it the slope of the line if it's a straight line. So we would learn that the slope is the change in the y value over the change in the x value. You might have also called it rise over run. And when you were looking at just a straight line, the rate of change of that linear function was the slope of the line, and the slope of the line is constant. It's the same everywhere. Didn't matter what 2 points on the line you used to calculate it, you would get the same rate of change, the same slope, and you probably had a formula for calculating the slope, something like y2 minus y1 over x2 minus x1. Now, what a derivative is the rate of change of a function, but not necessarily just a straight line. We're talking about now what if our function does not have a constant rate of change? What if the graph is a curve? So there's not just one same constant slope everywhere on there. It's actually different everywhere. So we could start by picking 2 points and just using our slope formula, finding the slope between those 2 points. And what that slope would give us is the slope of this line that kind of goes through next to the curve, but it's not the same as the curve. So this what would be a secant line. And if we find the slope of this secant line that passes through the curve at 2 points, then we get kind of an approximation or a slope that's close to the slope of the curve at the particular point that we're interested in. So that's another difference here with a derivative. We're talking about what is the slope at a single point as opposed to the slope between 2 points. So if you find this slope here of the secant line, you're getting an average rate of change. You can use that slope formula, maybe just change it to be function notation. So if this is the function f of x, then the average rate of change on the interval from, let's say that equals a, and then this x value here, we'll call that b. So the average rate of change would be f of b minus f of a over b minus a. And that's just y2 minus y1 over x2 minus x1 if a and b are the x's. And so again, that's an average rate of change, and that's just like an approximation. That's just something that you could kind of get a general idea of the slope of the curve itself. And you can see between these 2 points, the line and the curve are kind of similar. I mean, obviously the curve isn't straight, but as far as like the slope, how steep it is, they're pretty close. So it is an approximation. The closer together these 2 points become, the more accurate the approximation is going to be. So you can talk about this distance between the 2 points, the delta x, or the change in the x value. So you have the change in x between the 2 points. And the smaller that the delta x is, the more accurate your average rate of change, or the more accurate the approximation will be. It'll be closer to the actual rate of change, the actual derivative. Okay, so there's some notations that we could introduce for the derivative, and there were two mathematicians, Newton and Leibniz, and they both pretty much invented calculus at the same time, and so they each had their own way of writing things and their own names for things, and in most cases we actually use both of them because they have advantages and disadvantages. So certain situations it's better to use one versus the other. So Newton's notation for the derivative of a function was f prime of x. So the function f of x, the slope or the derivative of that function at a point x, would be written f prime of x. So this little apostrophe looking symbol is the prime. That's the derivative of a function at the point x. Leibniz built off of the delta y over delta x, the change in y over change in x, and this delta is the mathematical symbol for a change, and so he went with what we call a differential notation, where he changed the delta, which is a Greek d, to just a regular d, dy dx. And so now this represents, instead of the change between 2 points, an infinitesimally small change where we have this distance between the 2 points is basically become 0 where they're the same point, and then we get the derivative. And we call it a derivative in both cases. Newton actually wanted to call them fluxions instead of derivatives, but we went with derivatives for whatever reason. So we can approximate the derivative again. So f prime of x is approximately equal to this average rate of change, and there's kind of two ways you can look at it. We can approximate it by taking these two different points and finding the slope between them, like we talked about. So that would be f of b minus f of x over b minus x. So we're just calling the point that we're interested in, we're calling that x instead of a. So that would be b minus x. So this slope formula would give us an approximation for the derivative of a function at this point. Or we could also do the same thing by thinking of it in terms of starting at this point x here that we're interested in, and then going a certain distance further than that, this delta x distance, so we can add on a certain amount to that x coordinate. So we would start at the second point. The y2 would be x plus the delta x, and then the first point again is still f of x, and then the denominator here, the delta x is delta x. It's just the change in x. So I mean, these two, they're equivalent. They end up being the same thing. They're just two ways of kind of looking at it, two different ways of writing it, and they both give you the average rate of change, or the slope of the secant, or the approximate value of the derivative at whatever number x is for that function. So let's maybe do an example of that. Let's say our function is f of x equals x squared, just a real simple function here. And let's say we're interested in finding the derivative of that function of x squared at the point where x is 3. So what we're looking for is f prime of 3. So and we're going to approximate this using we'll use this version right here with the delta x, and or we can maybe do it both ways too. So again, the smaller delta x is, the closer it is to 0, or the closer together these 2 points are, the more accurate our approximation is. So we want to use a fairly small value of delta x to get a decent approximation. So we'll use delta x equals, how about 0.01. So then this approximation here would become 3 plus our delta x, 0.01, squared. So there's our f of x plus delta x, minus f of x, and our x is 3, so that would be 3 squared, over delta x, which is 0.01. So if we just work out this slope formula here, we would get our approximation. And just to show you, we could do it with the other version as well. So if this we're using the two different points, then our b would be 3.01. If we go a distance of 0.01 to the right of 3, and then it's still 3 squared. And then down here we would have 3.01 is the b, minus x, which is 3. So you can see it's the same thing, because when you subtract these, you get that, and you add those, you get this. It's just two different ways of writing the same thing, but you will see both versions on the AP test, so you need to be able to recognize both of them. And then as far as working this out to see what our approximation is, let's see if we can do this one here. If we square 3.01, use a calculator for that, but we should get 9.0601. And then of course 3 squared is 9, and then on the bottom we subtract and we get 0.01. So if we subtract these, then we get 0.0601 divided by 0.01. So dividing by 1/100th is the same as multiplying by 100, so that's going to give us 6.01 as the approximate value of the derivative. So what we're saying is that the derivative of our function here, and we can use Leibniz notation here, I'll show you too. So we could use that notation. We'd say dx, so the derivative with respect to x of the function x squared such that x equals 3, or at the point where x equals 3, is approximately 6.01. And so, given that that's our approximation, we might guess that the actual value is something like 6, and it turns out that 6 is the actual value. So, using a delta x of 0.01 gave us a fairly accurate approximation where we could see that the slope there is 6. And again, just to kind of visualize what it is that we found, if we look at the graph of x squared, which is our function, and we look at where x is 3, which is somewhere right about here, and if we were to think of the slope or the steepness, or we could even draw what they would call a tangent line here. So the tangent line is the line that is touching at that one point and has the same slope at that point. So the steepness of the curve x squared when x is 3 is equal to 6. And that's what a derivative is. It's just the slope of the curve. It's the steepness or the rate of change of the function at that one particular point, as opposed to between 2 points. And now so far all we've done is approximate it. We do need to be able to find the actual value. So how would we do that? Well, the smaller delta x is, the more accurate our approximation is. And so if we want a perfectly accurate approximation, then we need delta x to actually be 0. But the problem with that is, if we look again at our formula here for the average rate of change, or the approximation, if we let delta x equal 0, so that we're basically finding the slope between a point and itself, where it's just the same point, then we end up with f of x minus f of x over 0. So we end up with 0 over 0, which is an indeterminate. So we can't let delta x actually equal 0, but what we can do is take the limit as delta x approaches 0. And if we can find this limit as delta x approaches 0, then we would have the exact value of the derivative of the function at the point x. And that's exactly what we do to find the actual derivative. So let's do this one again. The f of x equals x squared, and we're going to find f prime of 3, so the slope of x squared at the point where x is 3. And this time we're going to find the exact value using a limit instead of just approximating it. So we're going to take f prime of 3 is going to equal the limit as delta x approaches 0 of f of x plus delta x, so that's going to be 3 plus delta x squared minus x squared, so minus 3 squared, over delta x. And now we just have to evaluate this limit here. So we can do it a couple of different ways. We can expand this binomial, or we could factor this difference of squares. I'm going to do it that way. So if we take the limit as delta x approaches 0, we factor the numerator here, we would get 3 plus delta x plus 3, and we would get 3 plus delta x minus 3. And then on the bottom we have delta x. So if we simplify that, we get the limit as delta x approaches 0 of delta x plus 6 times delta x over delta x. And we can see that our delta x will cancel now. Since delta x doesn't equal 0, it's merely approaching 0, we can cancel those delta x's. So we have the limit as delta x approaches 0 of delta x plus 6. And now if we use direct substitution and let delta x become 0, then we see that the exact value is 6, which is what we guessed based on our approximation earlier. So that is how you use this kind of limit definition of a derivative to calculate the derivative of a function. And we can, let's add the other version on there too. So this would be equivalent to, if you're using the two separate points, taking the limit as the second point b approaches your first point x. And this would be when you have f of b minus f of x over the difference between them, b minus x. So this another way of doing the same thing, basically, where they both are equivalent. And again, you'll see both kind of versions, and you need to recognize both of them. But there you go.